Hey there, it's Shannon Myers, and today we're checking out general vector spaces. So we have looked at vector spaces in Rn, but now we're extending that concept to things like polynomials, the set of continuous functions, matrices, all kinds of fun stuff. Let's start with our definition of a vector space. Let V be a set on which two operations, vector addition and scalar multiplication, are defined. If the listed axioms are satisfied for every vector u, vector v, and vector w in the set V, and every scalar c and d, then the set V is called a vector space. So for the first 5 properties, they're all for addition. So if you sum 2 vectors from the space, then you need to get another vector that's in the space. So that's what? Beautiful. Closure under addition. Now, what was another one we had? These are just like the ones for vectors. Beautiful. If you add 2 vectors, they're commutative. So you should also be able to get v plus u. So that's our commutative property. And then u plus quantity v plus w will be beautiful. Adding the vectors u and v first, and then adding w. And that is our associative property for addition. The set V has a 0 vector. We'll denote it like this, 0, with the arrow over it, such that what has to happen? Beautiful. For every vector V in the set V, if you add V plus that 0 vector, you should get the vector V back. That's the additive identity property. And then for every vector V in the set V, there's a vector in the set V denoted by negative vector V, such that V plus negative V equals the 0 vector, and that's our additive inverse. Groovy? All right then, scalar multiplication. So if you take a scalar times your vector u, that needs to be in our set V, our space V, and that's closure under scalar multiplication. And then c times the quantity u plus v would be c times u plus c times v, and that is our distributive property, one of them. Our next distributive property has to do with 2 scalars and 1 vector instead of 1 scalar and 2 vectors. And this will give us quantity c plus d times the vector u is equal to c times u plus d times u. And that's again distributive over addition. And then c times quantity d times u is equivalent to c times d times u. And that's our associative property for scalar multiplication. And then the scalar 1 times the vector u is equal to the vector u, and that's our scalar. I like to say scalar so that we don't confuse anything with other sets. So scalar multiplicative identity. All right, so let's move on to our first theorem, 3.1.1, properties of scalar multiplication. Let V be any element of some vector space V and C be any scalar. Then the following properties are true. So if you do the scalar 0 times V, you're going to get the 0 element in that space. So you have to remember that this 0 with the arrow over it could stand for many different things. You have to understand what space you're in, okay? And then a scalar times that 0 element for that set would again be the 0 element. And if you have C times V equal to the 0 element for that set, then C must be equal to the scalar 0, or V must be equal to the 0 element for that set. And negative 1 times V would be negative V. Cool, cool? Okay, so here we go. Determine whether the set, together with the indicated operations, is a vector space. If it is not, then identify at least one of the 10 vector space axioms that fails. So let's look at the set of all 2 by 2 matrices of the form S equals the matrix A, B, C1, such that A, B, C, and D belong to the real numbers. So what do you think? Well, why don't we check it out? If we let, I don't think it's going to work. And the reason I don't think it's going to work is because this 1 right here, it'll fail multiple things, but it'll definitely fail scalar multiplication and the closure property and the addition closure property. So if we let A equal to, now remember you need to pick a vector that's an element that's from that set. So it needs to be a 2 by 2 matrix, and it needs to have, I'll just call it 1, 2, 3, but I have to have this 1 here because that is what the set is defined as, the set S. All right? And then if we let C be equal to 2, what's going to happen? 2 times A is equal to 2, 4, 6, and 2. Notice that we don't get the desired 1 here, which is not an element of S. So S is not closed under scalar multiplication. Cool, cool? All right. Now, what about the set of all 2 by 2 non-singular matrices with the standard operations? So what is a singular matrix and a non-singular matrix? Beautiful. A singular matrix has what? A determinant which is 0, and a non-singular matrix has a determinant which is non-zero, right? So let's take a look at a counterexample because I don't think this is going to work, all right? So why don't we let A equal to, I don't know, our favorite, 1, 2, 3, 4. Notice that the determinant of A is equal to what? 4 minus 6, which is negative 2, which is not equal to 0. So A is non-singular. Now, what about this? If we have B equal to 1, 2, negative 3, negative 4, okay? The determinant of B is equal to what? Negative 4 plus 6, which will be equal to positive 2, which is non-zero. So B is non-singular. But let's look at the sum of A and B. So A plus B is equal to what? Well, you get 2 and 4, right? And then when we get a row of zeros, and remember, if you get a row of zeros, what happens to your determinant? It's 0, right? But we can work it out. You get 2 times 0 is 0, minus 4 times 0 is 0. Sorry. Which equals 0. So A plus B is singular. And what does that mean? That means that the set of all non-singular two by two matrices is not closed under addition. So we found a counter example. Cool, cool? All right. So now let's look at some more important vector spaces. We already looked at all of the Rn ones, right? R1, R2, R3, all the way to Rn, which are ordered n tuples. So now we get to some more. This first one represents the set of all continuous functions. Defined on the real number line. And then you also have a set of all continuous functions. So the C is for continuous functions. And this would be defined on a closed interval. From A to B inclusive. All right, P without a subscript is the set of all polynomials. If you have a subscript, P sub n, this is the set of all polynomials of degree less than or equal to n. So if you had P3, you could have a third degree, second degree, first degree, or a 0 degree polynomial. All right, so capital M sub Mn is the set of all M by n matrices, and then M sub Nn is the set of all n by n square matrices, which is redundant, but that's okay. All right, so for the second example, let's just take a look at what these zero vectors look like for these different spaces. All right, so in the set of continuous functions all along the real number line, well, what would the zero vector look like? What do you think? Set of all continuous functions. Well, what can you add to any function and get that function back? Beautiful. The zero vector would be some f of x equal to 0, or you could think of the line y equals 0, right? The horizontal line that lies on the x-axis. Cool, cool? All right, what about M14? So that's a matrix with, awesome, 1 row and 4 columns. So what would our 0 matrix be for that? Awesome. 0, 0, 0, 0. Okay, now what about for example 3? Describe the additive inverse of a vector in the vector space. So the way to think about the additive inverse is, hey, what do I need to add to this vector in order to get the 0 vector, right? So with the set of continuous functions, what would you be doing? Good. If you added negative f of x to any f of x, wouldn't you get the 0 vector out? Good. And then M14, and actually if we can say for f of x, right? And M14, if M14 was equal to A11, A12, A13, A14, right? Then our additive inverse would be what? Negative A11, negative A12, negative A13, negative A14, Or you could factor out the negative if you'd like, and that would be it. Cool, cool? Okay. So, determine whether the set of continuous functions is a vector space. All right? So here we go. We're going to need what? We're going to need 3 functions and 2 scalars, and I think it is. And one hint is I like put all 10 things down. Okay, so let's check it out. So we'll do our little setup here, and we'll say let F, G, and H belong to the set of continuous functions, and let C and D belong to the real numbers. Closure under addition. So what do we usually do for closure? Well, we take 2 vectors that are from the set, and then we add them together, and we see if we get something that's part of the set. So would you agree that some f at x belongs to the set of continuous functions? Beautiful. And then some g of x also belongs to the set of continuous functions, right? And then, I don't know if you remember way back when, but under the properties for continuous functions, what do we know? We know that this is equivalent to f plus g at x, which belongs to the set of continuous functions along the real line. So that works. Okay, commutativity under addition. So if I take f plus g at x, so we know, again, we're using a lot of the properties for functions. So this is equivalent to f at x plus g at x, right? But we know that that is equivalent to g of x plus f of x. And again, we're working with the set of continuous numbers. And so that in turn is equal to quantity g plus f at x. And so we've shown that one. Cool, cool? So let's take a look at f plus g plus h at x. Well, this in turn would be what? It would be f at x plus g plus h at x, which in turn would be f at x plus g at x plus h at x. Now, using the associativity property, we would then have f at x plus g at x, and then plus h at x. And then what? Awesome. This would give us f plus g at x plus h at x, which in turn is f plus g plus h all at x. So we've got associativity under addition. Good, good. All right, so additive identity. Well, if we take our f at x plus the 0 vector for the set of continuous functions, that's going to equal to f at x plus 0. And what is that? Beautiful, f of x. So we've shown that one. How about additive inverse? All right, well, if we have our f plus negative f at x, that's going to equal to f at x plus negative f at x. Cool so far? Which is 0, but isn't that the 0 vector for the set? So we're good. Now we get to the multiplication properties. closure under scalar multiplication. So if you have a scalar times f of x, what is this equal to? Beautiful. That's equal to c times f evaluated at x, which belongs to the set of continuous numbers on the real line. All right, distributivity under scalar multiplication. So for this one, we'll start with having the one scalar and two vectors. So what would we start with? We'd start with c times f plus g, all of that at x. That's going to equal to what? Beautiful. C times f plus g at x. That in turn equals to c times f at x plus g at x, right? Which equals to c times f at x plus c times g at x. And we've shown it. All right, next up we have distributivity under scalar multiplication with two scalars and one vector. So if we have c plus d times f, that's all at x, that's going to be c plus d times f at x, which is equal to c times f at x plus d times f at x, which is what we needed to show. All right, associativity under scalar multiplication. So if we start with c times d times f at x, that's going to give us c times df at x, which is c times d times f at x, which is c times d times f at x, which is c times d times f all at x. Cool, cool? All right, and then scalar multiplicative identity. Well, all right, so if we take a look at 1 times f at x, that's going to equal to 1, and then times f at x, which is just equal to f at x, so we've shown that. And conclusion, what do you think? Well, they passed all the tests, right? So the set of continuous numbers on the real line is a vector space. So we can consider that to be a known vector space. And since we know it's a vector space, then we can find subspaces, right? All right, so for this example 5, determine whether the set W is a subspace of the vector space V with the standard operations of addition and scalar multiplication. So if V is the set of continuous functions on the closed interval from -1 to 1, and W is the set of all functions that are differentiable on the closed interval from -1 to 1. So let's see. What do we need to say? Well, W is a non-empty subset of V. And how do we know that? Since differentiability implies implies continuity. Remember, it doesn't go the other way around. But this direction is true. All right? So now, if we go ahead and we let F and G belong to W and C belong to the real numbers, let's see what we have. All right, so let's look at this. d dx of f at x, right, plus d dx of g at x, would you agree that both of those terms belong to W, right? So we want to show that their sum belongs to V. So let's see what we get. Well, this would be equal to, beautiful, d dx of f of x plus g of x, or by properties of derivatives, which in turn is equal to d dx of f plus g at x. Make sense? So we have closure under addition. Now, d dx of, actually, c times d dx of f of x, right? What would that equal to? Well, that equals to d dx of, you can bring the scalar in, right? C times f of x, which in turn is d dx of what? cf at x, right? So we've shown closure under scalar multiplication. So, therefore, W is a subspace of V. What about this next one? V is the set of all continuous functions on the real line, and W is the set of all negative functions, meaning that f of x has an output that is below the x-axis, less than 0. So, okay, I don't think this is going to work. And there's more than one reason, but I'm going to use scalar multiplication. So if we let f of x equal to negative x squared, would you agree that that belongs to the set W? And we'll let c be equal to negative 3. Cool, cool? What do you think? C times f of x would equal to negative 3 times negative x squared, which is equal to 3x squared, and that is always going to be greater than or equal to 0. Right? So, W is not closed, is not a subspace of the set of continuous functions on the real line, since W is not closed. Under scalar multiplication, okay? All right, part C. V is the set of continuous functions on the real line, and W is the set of all odd functions. And remember, a function is odd if f at negative x is equal to negative f at x. So let's check it out. I think this one's going to work, and the reason why I think it's going to work is because it's got rotational symmetry about the origin. So let's just do it in general and see what happens, okay? So what do we have to say? Beautiful. We have to say that W is a non-empty subset of V. And if we let f and g be odd functions, and we'll let c be a scalar or belong to the real numbers, however you want to say it. Okay, so let's see what we get. If we add these, right? So f plus g at negative x is equal to what? Beautiful. F at negative x plus g at negative x. Good so far? But since f and g are both odd, this is going to be negative f at x plus negative g at x, which in turn is negative, if we factor out a negative, f at x plus g at x, which is negative f plus g at x. And so we have closure under addition. Cool so far? All right, now c times f at negative x is good. C times f at negative x, but that's equal to c times negative f at x, since f is odd, which is equal to negative c times f at x, which is equal to negative cf at x. And so therefore we've got closure under scalar multiplication. So therefore W is a subspace of V. Cool, cool? All right. And part D, the set of square matrices of order n such that n belongs to the positive integers. That's our big set. And then W is the set of all n by n diagonal matrices. So what do we think? So this just is basically all the possible diagonal matrices, right? As long as n is an integer, which makes sense. So what do you think? If you add two diagonal matrices, do you get a diagonal matrix out? Yep. What if you have a scalar times a diagonal matrix? Do you get a diagonal matrix out? Yes. So let's show it in general. We know that W is a non-empty subset of all square matrices, right? And so if we let A equal to Aij and B equal to Bij, such that, well, we want them to be diagonal matrices, right? So we want Aij and Bij belong to the real numbers, and what else? Aij equals Bij equals 0 for I equal to j. If it's not a diagonal entry, we want it to be 0. Cool so far? And then we also want to let C belong to the real numbers as well. All right, so let's see what we have. Well, A plus B is going to equal to Aij plus Bij, which is equal to one happy matrix of Aij plus Bij. And what's going to happen? You'll get zeros except for potentially everywhere along the diagonal, right? So this is going to belong to which is an element of W, right? So we're good. And then C times A would be equal to C times Aij, which would be, bringing in the C, you'd have C times Aij, and you'll get zeros everywhere except for on possibly the main diagonal. So this is going to also belong to our set W, right? So we would say what? Therefore, W is a subspace of V. Good so far? Awesome. Okay, next up, W, the set of all n by n matrices whose trace is non-zero. So the trace of a matrix is the sum of its main diagonal entries, okay? So we're looking at the big set is the set of all square matrices where you have order n, where n is a positive integer. So I don't think that this is going to work because you can either multiply by the scalar 0 and then you'd end up with a zero trace. You could add two matrices that have diagonal entries that are opposites of each other. So if we let A equal to 1, 2, 3, 4, right? And C equal to 0, the trace of A is equal to 5, which is not equal to 0. So A is an element of W. Sorry, I have these mixed for some reason. It doesn't really matter, but okay. And then if I multiply by 0, so C times A would equal to 0 times 1, 2, 3, 4, which gives us our 0 matrix, 2 by 2 matrix. And the trace of 0 times A is equal to 0. So we can say that W is not a subspace of V because W is not closed under scalar multiplication. Cool? Okay, so now our next example in this, where the big set is the set of continuous functions on the real line, and then W is what? Beautiful, the set of all linear functions in the form of ax plus b such that a and b belong to the real numbers and a is not equal to 0. Cool so far? Okay, well, what do you think? There's a lot of things that might not work, but one of them in particular could be, why don't we let f of x equal to negative x plus 2, and g of x could equal to x plus 5. So if I add the two of them, which would you agree are both from the set W, right? If I add f of x plus g of x, what happens? I would get negative x plus 2 plus x plus 5, which is 0x plus 7, which is not an element of W. So W is not a subspace of V, since W is not closed under Okay, so for part G, what do you think? I don't think this is going to work. Okay, so if A was equal to 2, 0, root 2, and B was equal to 3, 0, root 3, do you agree these both belong to the set W? Okay. Now let's look at A plus B. So that would end up being 2 plus 3, 0 plus 0, and then root 2 plus root 3, which is equal to 5, 0, root 2 plus root 3. And remember that root 2 plus root 3 is not equal to root 5, so it fails. Okay? So W is not a subspace of V, as W is not closed under addition. All right, so now example 6. Let's look at these two matrices. A is equal to 2, negative 3, 4, 1, and B is equal to 0, 5, 1, negative 2. So we want to go back to the whole linear combination idea, and we want to figure out whether this matrix 6, negative 19, 10, 7 is a linear combination of the given matrices A and B. So what would we do? So you could think of it like this. V1 is A and B is V2, right? When you're thinking about your linear combination definition. So here, what do we want to know? We want to know is we called this equal to some Z, right? We want to know, does C1 V1 plus C2 V2, does that equal to Z? Well, let's plug it in. So you'd have C1, and then V1 was the 2, negative 3, 4, 1. So it looks different, but you do it the same as with the regular row vectors. And then C2 would be times 0, 5, 1, negative 2. And you got to figure out, is there some way to equal to 6, negative 19, 10, 7? So how do we do this? Beautiful. 2C1 plus 0C2 has to be 6. Negative 3C1 plus 5C2 has to be negative 19. 4C1 plus 1C2 has to equal to 10. And then 1C1 minus 2C2 has to be 7. So what would we get? So we would end up getting that C1 would have to be equal to 3 from this first equation. And let's see what that, if it works for all of them. So this would give us that C2 would equal to what? And if I plugged in 3 for C1, we get negative 9. So we'd end up, well, let's do it this way. So 5C2 would have to be negative 10. So C2 would have to be negative 2. And let's see if it works. So then is 4 times 3 plus 1 times negative 2. Is that equal to 10? And yes, 10 is 10. 10, so that checks out. Now we just have to see if this other one checks out. So is 1 times 3 minus 2 times negative 2, is that equal to 7? So on the left side, 3 plus 4, yep, we get 7 is 7. So what did we find out? We found out that 3 times 2, negative 3, 4, 1 minus 2 times 0, 5, 1, negative 2 equals 6, negative 19, 10, and 7. Okay, so next up, now we're going into polynomials, all right? So actually, did we answer the question? Not quite, right? So yes, it can be, and that's the linear combination. All right, so consider P sub n at x would be, well, a0 times x to the 0, which is just 1, plus a1 times x to the 1, well, x to the 1 is x, and then plus a2 x squared plus a3 x cubed plus dot 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 plus a sub n x raised to the n. Cool so far? All right, so just for example, if we had p sub 2 of x, that's all polynomials of degree less than or equal to 2. So you get a0 plus a1x plus a2x squared. Cool, cool? Okay, so here you're given this set S, and we want to know whether the set of vectors in P2 is linearly independent or linearly dependent. So remember, what you want to do is set up the homogeneous system of equations. So here, this is like our V1. The second term is our V2. So remember that to check linear independence, you would do this linear combination and set it equal to the 0 vector. All right, so what would we get? We get C1 times x squared plus, sorry, this would have been C2, plus C2 times x squared plus 1 equal to the 0 vector for polynomials, which is just 0. And remember, I don't know if you remember like partial fraction decomposition, but you end up adding in the 0 terms for what you need, and you end up equating coefficients. So here, let's see what we're going to end up with. We're going to have C1x squared plus C2x squared plus C2. So do you see that we'll have a constant term and an x squared term? So let's take a look. We'll need a 0x squared, right? And we'll need a 0 for the constant. And that's still just equal to 0, so we're good. So now if I factor out the x squared to the right, and then I still have my C2, which doesn't have any x's with it, and then I set it equal to 0x squared plus 0. So I'm equating the coefficients. So C1 plus C2 would have to be equal to 0. And then what would my next one be? Beautiful. C2 would have to equal to 0. So what do we get? If C2 is 0, then C1 would equal negative C2, which is equal to negative 0, which is just 0. So what's my conclusion? Well, C1 equals C2 equals 0. So S is linearly independent. All right. So for example 8, determine whether the set of vectors in M22 is linearly independent or linearly dependent. So again, we're dealing with the same ideas here, but we're just using funny looking vectors or different vectors from vectors in Rn. All right, so why don't you, hopefully you've been pausing the movie and then working them yourselves to see how you're doing. But why don't we for sure try that on this example and go from there. All right, let's see how you did. So what do we want to do? We want to have, if this is like our V1, V2, and V3, we want to set up a situation where we have C1 times V1 plus C2 times V2 plus C3 times V3 equals our 0 vector. So that would give us C1 times 2, 0, negative 3, 1 plus C2 times negative 4, negative 1, 0, 5 plus C3 times negative 8, negative 3, negative 6, and 17 equal to the 0 vector for R2. Cool, cool? All right, and then setting up the system, we'll have 2C1 minus 4C2 minus 8C3 is 0. And then 0C1 is 0, minus C2 minus 3C3 would be 0. Negative 3C1 plus 0C2 minus 6C3 would be 0. And then 1C1 plus 5C2 plus 17C3 would also be equal to 0. Cool, cool? Okay, so let's see what we have. You could certainly set up a matrix. I'm kind of seeing a couple of ways to look at this. Do you see from this second row, you'd get what? You could solve this in terms of C3. So C2 would be negative 3C3. And then in the second row, you could also put that in terms of C3. So C1 would end up being, I think, negative 2C3. Is that okay? And so then, plugging these into the top equation, you'd have 2 times negative 2C3 minus 4 times negative 3C3 minus 8C3 would be 0. And I got these from here. And so then this would give us what? So we'd end up here with 0, C3 is 0, so 0 equals 0. So that means C3 could be anything, right? C3 can just vary. So if we were to let C3 equal to 1, say, then that would mean that C2 would be negative 3 and C1 would be negative 2, right? And that would mean what? That there's a non-trivial solution, right? So this means C3 can be any real number. So one possible solution is C1 equals negative 2, C2 equals negative 3, C3 equals 1. And there's infinitely many. So, since there exists non-trivial solutions to this homogeneous equation system, S is linearly dependent. All right. Okay, so for example 9, write the standard basis for the vector space. So in general, what would M32 look like? Well, you'd have a matrix, right, with 3 rows and 2 columns, right? So you'd have like A11, A12, A21, A22, A31, A32, right? And so remember when we were dealing with standard bases for Rn, you basically put a 1 in for one component of the vector and zeros everywhere else, and you go through and make a set containing of all possible ways you can do that exactly once. So our standard basis would be, what do you think? So we'll say S for our standard basis would be, so 1, 0, 0, 0, 0, 0 was one of them, right? What do you think the next will be? Beautiful. We could do 0, 1, 0, 0, 0, 0. The order of these doesn't matter. And then after that, 0, 0, 1, 0, 0, 0. And then 0, 0, 0, 1, 0, 0. 0, 0, 0, 0, 1, 0. And lastly, 0, 0, 0, 0, 0, 1. Cool, cool? So this here is our standard basis for the set of all possible 3 by 2 matrices. Okay, now P3. So if you think about P3, right, isn't that A0 plus A1x plus A2x squared plus A3x cubed? Okay? All right, so just like before, in turn, you want to let each of the coefficients, one of them equal 1 and the rest equal 0. So our standard basis ends up being, well, 1 plus 0x plus 0x squared plus 0x cubed is just 1. And then 0 plus 1x plus 0x squared plus 0x cubed would be 1x. And then 0 plus 0x plus 1x squared plus 0x cubed gives us x squared. And then finally, we get our x cubed. So let's take note of these, these bases. So do you see the standard basis for P3 has 4 vectors? So every basis for P3 will have, awesome, 4 vectors. And then the standard basis for the set of all 3 by 2 matrices had what? Awesome, 6 vectors. So therefore, all matrices of size 3 by 2 have a basis with 6 vectors. And look, isn't 3 times 2 6? Maybe that might be helpful. All right, so example 10, determine whether S is a basis for the indicated vector space. So let's count how many vectors we have. So there's V1, V2, V3, and V4. So there's 4 vectors in there, and the standard basis for P3 has 4 vectors. So I like often checking for linear independence first, right? So C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 would be the 0 vector. This is checking to check for linear independence. All right, so we would have C1 times 4t minus t squared plus C2 times 5 plus t cubed plus C3 times 3t plus 5 plus C4 times 2t cubed minus 3t squared. And that would be equal to 0. As a zero vector for P3 is 0. Okay, so then let's go ahead and just kind of multiply these through. So we'd have C1 times 4t minus C1 times t squared plus C2 times 5 plus C2 times t cubed plus C3 times 3t plus C3 times 5 plus C4 times 2t cubed minus C4 times 3t squared equals 0t cubed plus 0t squared plus 0t plus 0. All right, so starting with factoring out the t cubed to the right, let's see what we'll have. We'll have a C2, and then we'll have plus 2C4. And then, now I'm on my t squared. And so we'll have a negative C1. And then what? Minus 3C4. And then our t to the 1 will be 4 C1s. And then plus 3 C3s. And then finally we'll have, for our constants, we'll have 5C2 plus 5C3. And that's equal to 0t cubed plus 0t squared plus 0t plus 0. Cool, cool? All right, so then now we'll set up the system. So we'll have C2 plus 2C4 is 0. So I'm equating this guy to this guy, and then we'll have negative C1 minus 3C4 is equal to 0. And that's from equating that expression there equal to 0. And then we'll have 4C1 plus 3C3 equal to 0. And that's from equating this expression equal to 0. And then 5C2 plus 5C3 equal to 0. And that's from equating this expression to this 0. Cool, cool? A, our coefficient matrix, is going to equal to 0, 1, 0, 2, negative 1, 0, 0, negative 3, 4, 0, 3, 0, and then 0, 5, 5, 0. Cool, cool? Okay, so we're going to do two things. We're going to find our REF for A. So if we go back to second matrix, math, and then our REF, second matrix A, we'll get this result here, okay? And then let's also take a look at what the determinant is. Okay, so we'll do the determinant of A. This would be for spanning. when I entered in that matrix, when you have a homogeneous system, you don't have to enter in the last column of zeros. You just need to know that you have an augmented, matrix. So you have to know that there's that extra column of zeros. So really what happened was I had 0, 1, 2, 0, 2, 0, right? If I made it augmented. And then I had -1, 0, 0, -3, 4, 0, 3, 0. These all have zeros at the end for the constant part. And then 0, 5, 5, 0, 0. So the RREF of this ended up giving us 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. So I'm adding that column of zeros in. But notice that you don't have to enter it. Isn't that cool if you have a homogeneous system? So what does that mean? That means we got C1 equals C2 equals C3 equals C4 equals 0. So we found out that what? Our set S. So S is linearly independent. Now, the determinant of our coefficient matrix A, we got 30, which is not equal to 0. So there exists a unique solution to the system. Which means what? So S spans. And it would span P3. Therefore, S is a basis for P3. Since it's linearly independent and it spans. Now, just so you can note, so this part here was checked for spanning. Just a note though, there were 4 vectors in the set S, and there's 4 vectors in the standard basis for P3. So all we had to find, remember, was that it was linearly independent or that it spanned, and we could put that together with the dimension, right? Because the dimension of S would equal to 4, which is equal to the dimension of P3. All right, so you could have you could have done it a different way with just checking one thing. All right. Okay, so now we actually have 2 number 11s. It's so special. We'll call that second one 12. So now let's find a basis for the vector space of all 3 by 3 symmetric matrices, and then we'll find the dimension. So how did we find dimension? Beautiful. We found the standard basis for the set, and then we counted the number of vectors in the standard basis and got the dimension. So the trick to something like this is you have to know, well, what does a 3 by 3 symmetric matrix look like? Well, if we say that A is equal to any vector that's in that set, well, if I say this is A11, A12, A13, what has to be true? I mean, the A22 and the A33 are good, right? And this would be A23. But for symmetry to happen, don't we need to have kind of that mirror image thing going on? So this here would be A12. This here would be A13. And then we'd have A23 in order to satisfy symmetry. Okay? So with that in mind, let's find a standard basis, right? So the standard basis we'll call S, right? Would then, for the set, would be, well, we would have, if we started with a 1 there on the diagonal, we'd have zeros everywhere else, and we still met our requirement for symmetry. And then if we did 0, 1, 0, there has to be a 1 here. Cool so far? And then if we did 0, 0, 1, we'd be all right here, but then you'd have to have a 1 in the third row, first column, to satisfy symmetry. And then 0, 0, 0, we've already done the one where there's a 1 right here, right? So we don't do it twice. We'll put, we have to do something which is different. So just let that be 0 and then do a 1 in that diagonal. We've got another 1. And then continuing. I don't think we've done that yet. Nope. So then we'd have 0, 1, 0. And then what would our last one be? 0, 0, 0, 0, 0, 0, 0, 0, 1. Cool, cool? So just to, just to recap, we figured out what the heck a 3x3 symmetric matrix looked like in general. And then we put a 1 in each spot. But since, you had the symmetry requirement, it looked a little different. Some of them are going to have 2 1s in there to complete the symmetry requirement. So what's the dimension of the space? The dimension of our basis set S is, beautiful, 6, because there's 6 vectors in the set. Cool? All right. So number 12. Let T be the linear transformation from P2 into R, given by the integral T at P equals the integral from 0 to 1 of P of x dx. Find the preimage of 1. That is, find the polynomial function or functions of degree 2 or less such that T at P equals 1. So let's put this all together, okay? First of all, we're going from, our transformation is going from what? Beautiful. We start with a polynomial of degree 2 or less, and we go to the set of real numbers. So, well, that means that if you put some polynomial of 2 or less in, you get out a real number. Good so far? So, let's see what we've got going on. We were given that T at P is equal to the integral from 0 to 1 of P of x with respect to x. We've also been given what? We want to find the preimage. We want to find what goes inside the transformation. So we know that the output when we plug in P to the transformation is going to be the integral from 0 to 1 of P of x dx. Okay? But what P of x do we use? We're working in P2, aren't we? And so it would be the integral from 0 to 1 of, beautiful, a0 plus a1x plus a2x squared with respect to x. All right, so let's just look at what we matched up. So the output when we plug in P to our transformation is 1. And we also know that P of x, when we're dealing with polynomials of degree 2 or less, takes on this form. Cool so far? So let's do it. You know how to do this, right? The i's you would hold as constant, and then you would integrate with respect to x. So you'd end up with a0 times x plus 1/2 a1x squared plus 1/3 a2 x cubed. And that's evaluated from x equals 0 to x equals 1. So continuing this equation, you'd have 1 equals, well, a0 plus 1/2 a1 plus 1/3 a2 for the upper limit. And then do you see the lower limit? You get all zeros because you're plugging in x is 0. So we would get 1 equals a0 plus 1/2 a1 plus 1/3 a2. Well, why don't we isolate a0? So if we isolate a0, what will we get? Well, we will get 1 minus 1/2 a1 minus 1/3 a2. Okay, so when we're parameterizing a polynomial, the convention is this. We usually clear out the fraction part, and then instead of having like a1 and a2, we'll have a and b. So if we were to let a1 equal to negative 2a and a2 equal to negative 3b, let's see what we have. Well, a0 would then be 1 plus a plus b. Do you see that? Okay. And then, of course, we had that a1 was equal to negative 2a and a2 was negative 3b. So then you put it all together. So p of x, remember, is equal to a0 plus a1x plus a2x squared. So our p at x will be, well, a0 is 1 plus a plus b, and then plus 2ax plus 3ax squared. And then this is a set, right? So then we describe our set such that a and b belong to the real numbers. Cool, cool? All right, so that wraps it up for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.